Suppose we have done the casting, then if you look at the casting interior, you will find it is not uniform, the quality is not uniform, the inclusions are not uniformly present because of the nature of the solidification, because how continuous casting take place, the entrapments, the distribution inside the slab or bloom or billet inside the cast product is not uniform. Like even in ingot it is not uniform, in certain portion of the ingot you have more contamination, more inclusions. In the continuous cast product also, whether it is slab or bloom or billet, certain areas have more entrapments, certain areas have relatively less. Now I will try to come to that one by one. Start and end of casting, why there will be more inclusions? Because those at those point of time there is a possibility of deoxidation, because you are just putting the shroud, argon shrouding has just started, so some amount of reoxidation is possible. So these are a distinct possibility at the start and end of casting. Then another problem is the tundish slag. As I have told you, you do not allow the tundish to get emptied at the end of the casting, because the tundish has liquid steel and on top of that there is slag. So if you totally empty the tundish when at the end of the casting, then what happens? The slag, tundish slag also try to get inside the mold, which is not desirable. So some amount of some amount of liquid steel should always be kept inside the tundish. So this is facilitated when we are using dam and wear. That means we are not wasting too much of liquid steel in the tundish, because dam and wear we try to contain, try to reduce the amount of liquid steel which can remain in tundish. So the tundish slag should not be allowed to come under any condition within the mold. Then in steady state casting means you have started the casting, the speed slowly you have increased the speed and the speed is remaining constant. So that stage is called steady state casting. So during that stage there is a possibility, though not much high, the possibility is relatively less in steady state casting, but there is a possibility of mold slag entrainment in liquid steel. As I have told you, the interfacial tension, the viscosity, all these play a role, because at the interface even if there is small amount of turbulence, there is a possibility of liquid slag getting entrained in liquid steel. So the characteristics of the mold powder is very important, from which mold slag is getting generated. Interfacial tension should be slightly higher, viscosity should be whatever viscosity, optimum viscosity should be there, so that this does not get entrained. Then at the time of ladle changeover, I have told you in continuous casting one ladle goes, another ladle comes, but the casting continues because there is a buffer called tundish. But at the time of ladle changeover, there is a possibility of ladle slag which is coming inside the tundish. So as I have told you, you must not allow ladle slag to come. So the detection of ladle slag at the end of ladle, at the stage of emptying the ladle, changeover ladle is very important, or we have to keep some liquids. When there is no detection, as I have told you earlier, we have to keep some amount of liquid steel in the ladle so that the slag does not come. Then another important thing is sudden change in meniscal level of speed. As I have told you, there is a possibility of mold slag or even powder. So the possibilities of entrapments are not uniform in the casting. So when you are from the casting, when you are finally rolling the cast product to get the desirable final product, whether it is hot roll or cold roll, if you look into their inside, you will find that there will be more defects in rolled products corresponding to start or end of casting. Just after the ladle changeover, there will be slightly more of defects. Whenever there was a sudden fluctuation during continuous casting, there will be more defects, exogenous entrapments. So this is important to understand and to keep in mind, that whatever product you are getting from continuous cast, slab or bloom or billet, it is not uniformly having good quality. Certain areas of it, certain portions of it are maybe having some problems. If you know what are those areas, then we can do something like start or end of the casting. What happens? The product which is the slab or bloom or billet, whichever is getting cast at that stage, we may keep it separate because it is marked. We do not allow them to go for a good quality product, because as I have told you, like like in our liquid steel, how much of total oxygen is there, that gives an indication how the cast product will be, whether it is good or bad, how the rolled product will be, it is good or bad. Similarly, we know that the cast slab or bloom or billet which has been cast at the start or end of casting, or whenever there was a little changeover, that portion of the casting there is a possibility it will be relatively of inferior quality. So, we may separate out those portions to get desirable quality of final product. So, this is important, because if we know what are the areas of the casting or which portion of the casting there is a possibility of less cleanliness, more inclusions, more entrapments. So, it is then if you know, then it is better we separate out those portions. It is possible nowadays, people do that, start of casting, end of casting, little changeover, people try to separately process it, keep it separately, because there is a possibility, and it has been shown also that yes, those areas are relatively inferior in quality. So, we have to be careful when we finally process the cast products, which portion of the casting we are processing. If we know that certain areas are relatively more prone to problem, more prone to inclusions, entrapments, more probable to have less cleanliness, oxide cleanliness, mode of entrapment, so we should process them separately. That is what is important. Now, let me just go through what are the complex oxides as large entrapments. I have told that large entrapments are not good in the cast product, because they might create surface defects, they might create additional problems. So, what are the complex oxides as large entrapments? Aluminum oxide, this can be what? This can be a oxidation product, this can be a reoxidation product, it can be a nozzle clogging product, it can be a refractory erosion product with minus silicon and manganese oxide. These have been, in fact, when I will come to it later on, we can measure what are the, or we can rather evaluate what are the constituents present in some defect areas. Suppose we have got a defect in a particular area of the product, hot rolled or cold rolled product, we can cut that portion, we can see it on the microscope, on the scanning electron microscope, to know what are the constituents present. So, from that study only we have found out that what are the complex oxides which can present as large entrapments. So, one is the aluminum oxide, this can be present due to reoxidation, due to nozzle clogging, due to refractory erosion. Then there can be a combination of calcium oxide, silicon oxide, aluminum oxide. What is that? Where from does it come? It is basically slag. It can be either ladle slag, either tundish slag or mold slag. Now, there is some relative difference. Ladle slag, you have more amount of calcium oxide, all of you know, maybe around more than 50% will be calcium oxide in the ladle slag. Tundish slag, it is slightly more rich in silicon oxide, because you are using rice husk, as I have told you. So, some amount of silicon oxide will come in the slag. Mold slag, some amount of sodium oxide is present, some amount of calcium fluoride is present. So, mold slag, the presence of sodium oxide, calcium fluoride, this indicates that mold slag might have get entrained. So, whenever you have calcium oxide, silicon oxide, aluminum oxide constituents in the defects, you know that it is basically the slag. So, you have to be then careful, you have to do some back calculation, you have to find out why it has contamination has taken place, what was the problem. Another entrapment, exogenous entrapment may be zirconium oxide, which is coming from the ladle's nozzle sand. I have told you we have to be careful about the nozzle sand, it should not be allowed to drop inside the tundish when you are opening the ladle. At the time of opening we have to be careful. So, basically it is rich in zirconium oxide. So, these are the complex oxides, exogenous entrapments which can get entrapped in liquid steel, and finally you may find them in certain portion of the continuous cast product. During rolling it will go inside the final product and will create problems, quality issues, there may be surface defects. All this we will discuss in details later on, but what I am trying to tell here, I have mentioned again, I have mentioned earlier also, and again I am mentioning that the entrapments which have larger in size, more than 100 micron or more, that result in surface lamination in rolled products. So, we have to be very, very careful about these entrapments, particularly large entrapments, which might come from reoxidation, from nozzle clogging, refractory erosion, from the slag, whether it is ladle slag, tundish slag or mold slag or nozzle sand. These are some of the exogenous entrapments, some of the sources of exogenous entrapments which create problem, quality issues, and which must be taken care of. We must be very careful to prevent these at the time of secondary refining, at the time of continuous casting. Everywhere we have to be careful, so that there is less possibility of entrapment, exogenous entrapment like reoxidation product, nozzle clogging product, refractory erosion product, slag from ladle, tundish and mold, they should not get entrapped or entrained in liquid steel. I talked about the mold, what are the precautions we have to take in the mold so that the exogenous entrapments do not take place. So, I talked about initially from the sub-entry nozzle, this is the way, this is the port through which liquid steel is coming out, and through this port argon also is coming being blown in, it is coming out in the liquid steel pool here. This is within the mold, this is the mold, copper mold, which is getting cooled. So, at the top of the liquid steel there is a liquid flux, we called it mold slag, and because of the oscillation of the mold which is necessary for the casting, continuous casting, safe continuous casting, smooth continuous casting, it is necessary. This part of the liquid slag is getting inside at the interface between the mold and the solid shell. This is also an important requirement. This helps the mold shell not getting stuck. So, sticking does not take place if there is a liquid inside. So, this is a solid powder, solid solidified slag, and this is the liquid slag. So, this is the flux rim, this is a flux powder, and just at the top of the liquid steel there is a liquid flux. So, as I had mentioned, the turbulence at the interface between the liquid slag and the liquid steel is very important. If there is too much of turbulence, there is a possibility of entrainment of the liquid flux or liquid mold slag getting entrained in the liquid steel. So, we have to be careful about that. This shows how this argon bubbles along with this liquid steel, how it is mixing, getting intermixed, and how the inclusion particles and bubbles, they are coming like this, sometimes going up, then finally coming down, and finally will go up like this. This is half of the mold, this is the SEN, this is one end of the mold, the other end will be somewhere there. So, only the half of the mold we are showing in this particular picture. So, the turbulence within the mold is very important, we have to be careful, thus there is not too much of turbulence. Too much of turbulence will cause possibility of mold slag entrainment. If there is too much of turbulence, again there is a possibility of flux or powder entrapment if too much of fluctuation of the surface, here the meniscus, this is called the meniscus. So, this is very important. Now, this I had mentioned that the design of the port is very important, because whether liquid steel should come down like this, or should the flow should be horizontal, or the port angle should look up, that means the flow should be slightly towards the air or above. So, this is also very important. So, modeling can decide what should be the turbulence, what extent turbulence can be tolerated. These are the issues which can be sorted out through modeling. Then I talked about what are the important measures in mold, like SEN, the sub-entry nozzle of suitable configuration and optimum submergence. These basically decide what is the level of turbulence, so that is very important. This facilitates flotation of NMI, non-metallic inclusions, whether they are getting generated, or if there are some exogenous entrapments, they should float up. The turbulence should be such that they should float up and get absorbed by the liquid slag, that is very important. So, this sub-entry nozzle configuration, port angle, and how it is, what angle it is there, what is the size, all this will decide what is the level of submergence. This will decide whether the turbulence is optimum or not. Then I have mentioned that instead of normal powder, we should use granulated casting powder, which has good flowability. Normal powder, there is a problem of getting coagulated, so flowability is a problem, but you have a granulated casting powder, it has good flowability. So, this helps in uniform powder coverage with less entrapment. This is very important. Powder coverage at the top should be, this powder coverage at the top should be uniform. This is required not only from the heat transfer point of view, it is also required from the point of view of uniformity of the casting. As a casting should be stable, stability of casting also it gives this flux, uniform flux powder will give uniform heat transfer and uniform uniformity in the casting operation. So, I have talked about the granulated casting powder, talked about the mold slag, we should have optimum viscosity and surface tension. This is required because if the viscosity and surface tension at the interface is not uniform, or is not optimum rather, there is a possibility of slag entrainment during steady state casting. Normal casting, there is a possibility of slag entrainment if the viscosity and surface tension are not very uniform, optimum. So, then I have mentioned that mold level fluctuation is very important, because first there is a movement of the mold in a vertical and downward direction, which is called mold oscillation. So, oscillation should be such, and the flow of the liquid steel from the SEN should be such that there is not too much of mold level fluctuation. So, this can be measured, mold level fluctuation. If there is too much of fluctuation, then there is a feedback, and this can control the level of movement, level of liquid steel movement. So, there is a possibility of controlling the mold level fluctuation. So, it has to be within certain limits, say within the limit of plus minus 2 millimeter mold level fluctuation. So, this helps in preventing slag or powder entrapment. If there is too much of fluctuation, there is a possibility of slag or powder entrapment. Then I had mentioned that sudden change in casting speed is not desirable. What happens if there is a sudden change in casting speed? That means too much of liquid will come out in this mold, which will again generate a lot of fluctuation. So, that is not desirable. So, therefore, what is important is to control the sudden change in casting speed. Once you reach the speed, desirable speed of say 0.8 or 1 meter per minute, the desirable thing is to continue with that. That is called steady state casting. There should not be a fluctuation in casting. That should be avoided under all circumstances. Then of course, this is very important, argon shrouding to prevent nozzle clogging. The port should not get clogged. There is a possibility of clogging here because there is small amount of dissolved aluminum in liquid steel. So, if there is air ingress, there is a possibility of formation of alumina. If there is titanium in liquid steel, there is a possibility of formation of titanium oxide. These are solid at the temperature of liquid steel. So, there is a possibility of clogging. So, argon flow is a must. This will prevent formation of alumina, titania, this type of oxides which are solid. So, argon flow, argon cover is very important. So, if we undertake all these precautions, if we do casting with all these precautions in the mold, then there is a possibility that not only entrainment of liquids or rather mold slag will be prevented, but there is a possibility of some amount of deoxidation is possible, some amount of total oxygen which will allow the inclusions to float to the surface and get absorbed by the slag. So, there is a possibility of minor reduction in total oxygen also. That means, there is a possibility of cleanliness level increase in mold as well. Then I had mentioned that the exogenous entrapments, what are the complex large entrapments? Aluminum oxide along with minor silicon or manganese oxide, they can be from the reoxidation product, from the nozzle clogging product, from the diffractory erosion product. Now, what happens when there is a nozzle clogging? If there is a nozzle clogging here, when there is a flow of liquid steel, that means the some amount of clogged material will be dislodged from the port and will get inside the liquid steel in the mold. So, that is a source of exogenous entrapment again. So, clogging not only creates a problem for the normal casting, but from the cleanliness point of view also there is a problem. So, we have to be careful about that. So, aluminum oxide or along with some minor silicon or manganese oxide, this is a typical entrapment which might come from reoxidation, might come from nozzle clogging, might come from refractory erosion products. Now, I have talked about the slag entrapment or entrainment. If the ladle slag comes, that is also not desirable. I have mentioned there has to be a proper control that ladle slag should not be allowed to get inside the tun dish. Then the tun dish slag also should not be allowed to come towards the end of the casting within the mold. Then the mold slag also should not be allowed to get entrained. By controlling the mold level fluctuation, by having suitable mold flux characteristics of suitable viscosity and interfacial tension, so that mold slag does not get entrained. Now, there may be a possibility of zirconium oxide, which is a ladle sand, I had mentioned you, nozzle sand, which has to be prevented from getting inside the tun dish when you are opening the ladle exit. So, these entrapments which are large, more than 100 micron, they result in surface lamination in rolled products. Thank you very much.